of the CMF's cone fundamentals and cone isolating stimuli tutorial. We had just gotten down to line 184 or so in the part 1 of this tutorial, where we had shown how you can construct cone isolating directions in the RGB tristimulus space by transforming the unit vectors in the cone fundamental space. Now we're going to take a look at that in some different ways. So what we're going to do is create a chromaticity diagram to visualize directions in the RGB tristimulus space. And in the chromaticity diagram, what we do is we normalize the tristimulus values by their sum, or in some other way to get rid of the intensive direction. And that preserves information about variation in relative tristimulus values, but throws away information about the magnitude. And what that's convenient for is it gives us a way in a chromaticity diagram to represent color stimuli where we ignore the intensive directions and get to look at a 2D plot rather than trying to visualize things in 3D, which is quite difficult. The function in Psych Toolbox xyz to xyy converts tristimulus values to chromaticity and, in that case, luminance by preserving the y value. But the first two rows of the returned column vectors give us the chromaticity coordinates corresponding to the input. And that routine was written for the conventions of the XYZ color space, but it does the same calculation on any tristimulus values, and so we can use it to compute an little RG chromaticity diagram from the big RGB tristimulus space. And in fact, I'm just going to make a little edit to this script here and use capital RGB there for tristimulus values. Okay, so we had, for example, computed we have the color matching functions for all the monochromatic wavelengths, and if we convert those to the chromaticity diagram, we'll have, it's often called the spectrum locus, we'll have the spectrum locus in chromaticity, and at 1 nanometer spacing or 10 nanometer spacing, depending on whether we put the 1 nanometer or 10 nanometer versions in. So let's go ahead and do that. I've run the script down to here already. And then let's just make a plot of that chromaticity diagram. And I'm going to actually make 3 copies of the plot for reasons that I'll want below, but they're all going to be the same for right now. And all this code here down through here just sets up the plot and makes the subplots. So I'm going to go ahead and run that. It's not deeply interesting how that works, it's just doing it. And so here are 3 copies of the spectrum locus in 3 subpanels of this plot. Each of these points, starting at the short wavelengths and going around to the longer wavelengths, represents the chromaticity of the tristimulus values for one of the monochromatic wavelengths that we started with. And it has a little bit of a horseshoe shape. You may be familiar with horseshoe-shaped spectrum loci. They look different in different chromaticity spaces or in different color matching tristimulus spaces, but here they are. Okay, so that's a way to visualize that. And one thing to keep in mind is that all physically realizable lights have to be a positive or convex combination of these chromaticities. So they have to lie essentially within this horseshoe and the vector line connecting the 2 endpoints at short and long wavelengths. Okay, now above we computed cone isolating directions, and stimuli that differ only in a way that is visible to one class of cones have the feature that for a dichromat who's missing that class of cones, those stimuli look the same or be confusable. So we can plot the chromaticities of the cone isolating directions in the chromaticity diagram, but to make them realizable, we have to add them to something. So in other words, we can add cone isolating directions of different magnitudes to distinguishable stimuli, and each of those will produce a different line in the chromaticity diagram. And stimuli that lie along that line for a dichromat will not be detectable because the dichromat is missing one class of cones. And you may have already guessed that the reason we made 3 panels of the chromaticity diagram is so that we could make 3 different sets of plots of confusion line for the 3 most common types of dichromats: protonopes, who are missing the L cones and therefore can't see L cone isolating stimuli; deuteranopes, who are missing the M cones and can't see M cone isolating stimuli; and tritonopes, missing the S cones, who can't see S cone isolating stimuli. And again, I'll fix a little typo here as we go along, add that parenthesis, and we'll compute those lines. Well, how do we do that? Well, we pick stimuli that are distinguishable, and we add in different amounts of the cone isolating stimulus. So here what we'll do is we'll start with each of the points on the spectrum locus at every 10 nanometer and compute a confusion line for each one of those. And you'll see in a minute that those actually converge to the chromaticity of the isolating direction for the corresponding cone class. And this comment again, I'm going to just fix it here for each cone class. And the intuition for this is pretty simple. As you add in more and more of the cone isolating stimulus to anything, you'll begin more and more to swamp the chromaticity of the thing you added it to as the magnitude of the added in cone isolating stimulus gets larger and larger. And the limit you added in a huge amount of intensity of that, wherever you started sort of becomes irrelevant, and the confusion lines all converge to the same point. So what we're going to do is first we're going to take the cone isolating directions and we're going to convert those to chromaticity, so we can plot those in the plot just to say where they are. So I'll do that. And then we're going to compute confusion lines for each of the points on the spectrum locus at 10 nanometer spacing. So I want to know how many that's going to be. There we go. And for each type of dichromat, which I'll delineate here by W, we're going to compute confusion lines. So W is going to loop through. We're going to have a color for the subplot, just to be fancy here, corresponding to the protanope, deuteranope, and tritanope. And the other thing is I got some hand-tuned numbers here, which just say how much of the cone isolating stimulus we have to add in to make the plot sort of come out looking reasonable. So it's not deeply substantive, but it is something you just have to set to make this work nicely. And then we're going to compute the confusion line. So we're going to have 100 points in each confusion line. And what I'm going to do is start with the point on the spectrum locus, the tristimulus values in the spectrum locus for each of the 10 nanometer spacing indexed by the number of confusion lines. That's I. And I'm going to add to that an ever-increasing amount where J here indexed the number of points. J is going to get bigger and bigger starting at 0. So I'm going to start right at the spectrum locus. I'm going to add in a fraction which goes up to 1 times the cone isolating tristimulus values for this particular type of dichromat, the L, M, or S. And I have this factor which is just going to multiply it. Something that you'll notice here is one of these factors is negative. And basically cone isolating stimuli, whether you increase or decrease the class of cones, are still cone isolating stimulus. The negative corresponds to decreasing. And depending exactly on how things project onto the chromaticity diagram, it turns out the plot looks more reasonable using a negative number here rather than a positive number. I haven't thought through the projective geometry of that super deeply. If you like thinking about these things, you can ponder it. And if you really understand it better, let me know. Okay, and then we're just going to take each of those points on the confusion lines and we're going to again convert to chromaticity. So let me do that. I'll just run this block of code here. We've just gone through. Great. And then we're going to add those to the plot that we already had. Just to go through, we're going to select each subplot. We're going to put the appropriate line on for each of the subplots, which goes a little separately. Sorry, the appropriate chromaticity of the cone isolating direction. And then we're going to add the confusion lines for that particular one. So that's again within this loop here. And so we'll add the confusion lines. And then tidy up the labels. So for each confusion line, we do that. And if I just select here and come all the way down to the end of this loop, just going to add those in, color them nicely, and we can bring them back here. So let's look at the one for the protan. The protans are missing the S cone. And so what we've done is we've added in the tristimulus values corresponding to this L cone isolating chromaticity here. We did the addition in the full tristimulus space, and we started by adding them to each of these black points on the spectrum locus, and you see them all here converging to the same point. That will be of interest to us in a future video where we talk about how color matches from dichromats can be used to lock down the linear transformation from color matching functions to cone fundamentals, but I'm not going to talk about that now. So this is sometimes called the copunctal point of the confusion lines. And experimentally, if you did color matches for dichromats, they will vary along these lines, and you can actually identify these lines experimentally. Here's the one for the deuteranope, missing the M cones, and the tritanope, missing the S cones. And so those are the confusion lines. And you'll see these plotted sometimes in textbooks, and I haven't always found the explanation of what they are that clear. And so I hope this clarifies for you what confusion lines are and what these chromaticity diagrams are here, chromaticity diagrams in the Stiles and Birch color matching space. You could do exactly the same exercise in the XYZ color matching space, and you would get the XY chromaticity coordinates rather than these RG chromaticity coordinates. Okay, I'm going to stop part 2 here, and we'll pick up again with part 3, where we think a little more about cone isolating vectors and visualizing them in 3D color spaces.